Good morning. Next is the comparison of electron density on benzene, methyl benzene, that is toluene, phenol, chlorobenzene, and nitrobenzene on the basis of different types of electron displacement in these molecules. So this is very important. Comparison of electron density on benzene, toluene, phenol, chlorobenzene, and nitrobenzene based on different types of electron displacement, that means inductive effect, mesomeric effect, hyperconjugation, etc. When you consider or when we consider all these factors, how it will determine the electron density on various type of molecules. Okay, now we can see that first is benzene. This is the structure of benzene. Okay, so next is we are taking toluene. That is this is so this methyl benzene. This is toluene. Now before I go to benzene, let us first come to toluene. We know that toluene, that means this is methyl benzene, and here it's an alkyl group. This is an alkyl group, and we have studied that alkyl group is having electron pushing effect or electron releasing effect, or alkyl group is having a plus I effect. This is the first point you have to keep it in mind. Alkyl groups are having plus I effect. That means electron pushing effect. It will push the electron towards the ring. Therefore, what will happen? You can see that this pair of electron will be shifted to here. Okay, that means here you can see that the structure will become like this. Okay, and that means here it will have a negative charge on this carbon. I am not drawing all the structures, and in the next stage what will happen? This negative charge will come, or a pair of electron will come between these two carbon. That time this pair of electron will be shifted to here. Here you can see that a pair of electron and a negative charge. In the next resonance stage, this pair of electron will be come between these two carbon, and this will be shifted to here. So here also you can see that a pair of electron and a negative charge, or in short you can see that ortho and para position. These two are ortho position and this is a para position. Because of plus I effect, we can see that the ortho and para positions are negatively charged in methyl benzene. This is one factor. Now next is, again I am explaining, so keep it in mind. In methyl benzene there is plus I effect is there, electron pushing effect is there. Therefore ortho and para positions will get a negative charge. Okay, now second factor, look at it here. Again I am writing methyl benzene or toluene, that is CH3. Here it is a ring. Last class we have discussed the same thing. Now you can see that this is double bonded carbon. Okay, so this carbon, since this carbon is attached to a double bonded carbon, this is alpha carbon, and these three are alpha hydrogen. That means these three alpha hydrogen can undergo hyperconjugation interaction. That means what will happen? Last class we have discussed, this bond will be shifted to here, correct? And therefore what will happen? This pair of electron, this bond is shifting to this carbon. So this carbon is getting a negative charge. So I am drawing the resonance structure. So here it will be CHH, and here it is H plus. Now I am explaining hyperconjugation in methyl benzene or toluene. Hyperconjugation. First we discussed plus I effect, and next is a hyperconjugation. So what will happen? Here it will become a double bond, and here you can see that this is our ring. Okay, this is our ring. Since this bond is shifting to this carbon is getting a pair of electron and a negative charge. These two bonds are here like this, and in the next step you can see that this pair of electron will be shifted to here. Then what will happen? This pi bond will be shifted to this carbon. So we get the next structure like this. Here no change, C H H, and here it is H plus double bond. Here is here it is like this, and here it will become a double bond. Since this pi electron shifting to this carbon is getting a pair of electron, and this double bond no change. Next stage, this will be shifted to here, so here it will become a double bond. Then this pi electron will be shifted to this carbon, and we get the next structure like this. See, here it is H, and here it is H plus double bond, and here you can see that again here it is a double bond, and since this pair of electron is shifting to here is a double bond. This pi bond is shifting to this carbon is getting a negative charge and a pair of electron. Now you can see that by hyperconjugation also, this is ortho position and this one is para position, this one is ortho position. Again ortho and para positions are negatively charged. That means if an electrophile comes, usually aromatic compounds will undergo electrophilic substitution reaction. Electrophile means a positively charged species. Therefore, if an electrophile comes to toluene, or the positively charged comes to toluene, where it will go? Definitely it will go at the para position or ortho position. Para position and ortho position, because by hyperconjugation and plus I effect of methyl group, hyperconjugation effect and plus I effect of methyl group, the ortho and para positions of toluene are negatively charged. Therefore, the incoming electrophile will definitely attack at the ortho and para position. That means it will not attack the meta position, because ortho and para positions are negatively charged. Therefore, the positively charged electrophile definitely will go to ortho and para position. Or we can say that these alkyl groups are methyl group. Alkyl groups are activating group. They are known as activating group because the ortho and para positions are more negatively charged. Therefore, the electrophile can easily attack at the ortho and para position. Such groups are known as activating group. So this is so now what is the comparison of the electron density on benzene, toluene? You can see that in toluene and in the case of benzene, these pi bonds are equally distributed, and hence you can see that all the position will have equal amount of negative charge or electron pair shifting. So what is happening? This pi is shifting to here. Okay, then what will happen? This will be shifted to here. This will be shifted. That means this is equal in all the position. Equal of amount of electron density in all the position in a benzene ring. But in the case of toluene, you can see that ortho and para positions will have more density, electron density than meta position, because of plus I effect and hyperconjugation interaction of methyl group. Next is so benzene and toluene is over, and next is phenol. Next is phenol. Look at it here, phenol. So next we consider phenol. Now we know that in phenol, oxygen is having lone pair electron. So outer electron is 6, 2 electrons. See, look at it here. Here it is OH. Outer electron is 1, 2, then 3, 4, 5, 6. Outer electron oxygen is 6. 1 electron is used for making this OH bond. Another electron is used for making this OC bond. So remaining 2 lone pair. This is OH. Okay, here it is OH and here it is this bond. This is phenol. Phenol is having 2 lone pair of electron. When there is lone pair of electron, what type of effect will be there? This will have a plus M effect, plus M effect. What do you mean by plus M effect or plus R effect? That means this will undergo resonance. This will undergo resonance. This pair of electron, this lone pair of electron will be shifted between oxygen and carbon. Then what will happen? This pi bond, this pi electron will be shifted to this carbon. This is what is called plus M effect, plus M effect, plus M effect or plus R effect. So in phenol, what type of electron displacement? Plus M effect. In methyl benzene toluene, what is that? Plus I effect, and what is that? Hyperconjugation interaction. And here you can see that plus M effect, this lone pair of electron is pushing into the ring, and you can see that next resonance structure, you can see that this will come like this. Okay, since this pair of electron is moved from oxygen, and here it will become a double bond. Of course, oxygen will get a positive charge because this pair of electron is moved here. Here it is OH. Okay, of course, this pair of electron is there only. Since this pair of electron is moved away from this oxygen is getting a positive charge, and now this pi electron is shifted to this carbon. That means it's a pair of electron, and of course will have a negative charge, and the remaining bonds are here only. Now in the next resonance structure, what will happen? This pair of electron will be shifted between these two carbon. That time what will happen? This pi electron will be moved to this carbon. You get the next resonance structure like this. Okay, here it is double bond OH and with a positive charge. Of course, here it will become a double bond. Since this pi electron is moving to this carbon, carbon is having a pair of electron and a negative charge. Here the double bond is like this. And in the next step, this pair of electron will be shifted between these two carbon. Then what will happen? This pi bond, this pi electron will be shifted to this carbon. We get the next resonance structure like this. Here it is double bond OH and it is positive charge, and here is a double bond, and since this pair of electron is moving here, it will form a double bond, and this pi electron is shifting to this carbon. The carbon is getting a pair of electron and a negative charge. And the next stage, what will happen? This pair of electron will be shifted to here. This will go back. This will go back, and the positive charge is removed. Again, here also you can see that because of plus M effect of OH group, because of the plus M effect of OH group, we can see that this is ortho position, this is para position, this is para position, and this one is ortho position. Again, we can see that the ortho and para positions are negatively charged. Like a methyl benzene, but the effect is different. Here the effect is a plus M effect. The plus M effect of OH group, the ortho and para position of phenol is negatively charged, and hence the incoming electrophile, the positively charged species will come and attack at the ortho and para positions, and hence the OH group, this is also activating group. This is also activating group because the ortho and para positions are negatively charged. Therefore, what will happen? Immediately the electrophile can come and attack. Okay, so this is also coming under activating group. OH group is also activating group. So here the operating effect is plus M effect. So first we have discussed benzene. In benzene there is no particular effect because in benzene all the double bonds are similar. So electron density is equally distributed. But methyl benzene plus I effect and hyperconjugation. Now here OH group phenol, what effect? Plus M effect is there. Next is chlorobenzene. Chlorobenzene. Okay, chlorobenzene. Again, we know that chlorine is electron withdrawing group. Electron withdrawing group, that means of course we are expecting a minus I effect, because chlorine is electron withdrawing group and we expect a minus I effect. It is there. Minus I effect because chlorine more electronegative, it will withdraw an electron, and hence there is a minus I effect, minus inductive effect is there. But at the same time, you must remember that chlorine is having lone pair of electron. Okay, its outer electron is 7. One electron is used for making this bond. Then it has 3 lone pairs. Now, because of the presence of lone pair electrons present on the oxygen atom, what type of effect is also possible? Plus M effect, plus M effect, plus M effect. So minus M effect means electron is withdrawing, plus M effect means electron is coming into the ring. Here you can see that plus M effect predominates minus I effect. Hence, what will happen? You can see that this plus M effect is more. Therefore, again, what will happen? This pair of electron will be shifted to here, and this pi bond will be shifted to this carbon. We get the next resonance structure like this. Here it is double bond Cl. Since this moving, if the electrons are moving from chlorine, chlorine is getting a positive. This pair of electron is there only, and we can see that this pi bond is shifting to this carbon. Carbon is getting a negative charge, and these bonds are here only. Like phenol, we get the next two resonance structure also. What is happening? The next stage, this will be shifted to here, so this will move to here, and this time that the next time this will be shifted to here, and this will come here. That means in chlorobenzene also there are minus I effect and plus M effect is there. Plus M effect predominates, minus I effect. So here also you can see that the ortho and para positions are negatively charged. The electron density on ortho and para positions are higher than that of meta position. Therefore, the electrophile will come and attack at the ortho para position in chlorobenzene also. Okay. Now last is nitrobenzene. Nitrobenzene. Look at it here, the structure of nitrobenzene. Okay, N double bond O, okay, and this is O. Nitrogen can make only 3 bonds, but the last bond is making using a lone pair electron. That means nitrogen is getting a positive charge and oxygen will have a negative charge. This is the structure of nitrobenzene, NO2 group. Nitrobenzene, actually what is nitrobenzene? What is that here? Nitrobenzene means this is NO2, this is nitrobenzene, and its actual structure is like this: N double bond O and single bond O, and nitrogen is having a positive charge and oxygen is having a negative charge. We have studied that NO2 group is electron withdrawing group. Electron withdrawing group, that means minus M effect, electron withdrawing effect, minus M effect. What do you mean by minus M effect? Look at it here. Here you can see that this pi bond is shifting to oxygen. Then what will happen? This bond breaks from this carbon and it will come here. Okay, so what we get? Look at it here. We get the structure like this. Okay, look at it here. Okay, and here the bond is like this, no change. Here it is like this. Now you can see that here it is En, and here it is O minus, here it is plus, and here you can see that since this pair of electron is shifting to oxygen, there will become a single bond, and oxygen will have a pair of electron and a negative charge. At the same time, what will happen? This pi electron will be shifted to oxygen. That time this bond breaks from this carbon, and it will come here. So here it will become a double bond. Since the bond is breaking from this carbon is getting a positive charge. Understood? Once again, now the bond is like this. The bond breaks from this carbon and it will come like this. So this carbon is getting a positive charge. Here it will become a double bond. Simultaneously, what will happen to this bond? This bond will be moved to oxygen. Oxygen is getting a pair of electron and a negative charge. Clear? In the next step, next structure, you can see that this bond breaks from this carbon, and it will be shifted to here. So what will happen? This is the bond, breaks from this carbon and it will come like this. So we get the next resonance structure like this. Okay, here it is like this, and you can see that the bond breaks from this carbon and it's shifting between these two. Here it is a double bond. Since the bond breaks from this carbon is getting a positive charge. The rest is as it is, no change. Here it is double bond, N, O, a pair of electron, and here it is O minus, here it is a positive charge. Clear? And in the next step, you can, or in the next structure, you can see that what is happening in the next structure. This bond breaks from this carbon and it will move to here. Okay, breaking from this carbon and it will be moved to here. So what will happen? This carbon is getting a positive charge and here it will become a double bond. So we get the next resonance structure like this. Look at it here. It is like this, and here is a double bond, and this bond is here. And since the bond is breaking from this carbon is getting a positive charge. Okay, keep it in mind, when this bond comes to here, this positive charge is removed. When here is a double bond, the positive charge is removed. When this bond move to here, the positive charge is removed and a positive charge is created on this carbon. Now the rest is as it is, N, and here it is O minus, and here is also O minus. Of course, oxygen is having nitrogen is having a positive charge. Okay. In the next step, what is happening? You can see that this double bond, one double bond is formed here. That double bond will go back. Okay, one of the bonds, this pi bond will be moved back. Okay, that time what will happen? Our pair of electron on the oxygen atom will come back, and what we get a structure like this. Okay, here it is double bond. Since this bond breaks from nitrogen and it is moving here, again here it will become a double bond, here it will become a single bond, and here again it will become oxygen, double bonded oxygen. Here it is O minus and a positive charge. Anyway, look at it here, because of minus M effect, minus R effect, we can see that the ortho position, para position, again ortho position, the ortho positions and the para position in nitrobenzene is positively charged. That is important here. The ortho and para positions are positively charged. Therefore, the incoming electrophile, again keep it in mind, electrophile is having a positive charge. The incoming electrophile cannot attack at the ortho and para position, because ortho and para positions are also positively charged. Therefore, there will be repulsion between this position and the incoming electrophile. Therefore, in nitrobenzene, the incoming electrophile will attack at the meta position. In meta position, you can see that the meta position is not positively charged. Okay, nitro group, NO2 group. Here you can see that these two are ortho position, and this is meta position. This is para position. You can see that this is ortho. And this is meta. Again, para is positively charged. In meta, there is no charge. Therefore, what will happen? The electrophile will attack at the meta position in nitrobenzene because of minus M effect of NO2 group. Okay. So these are the comparison of electron densities on different types of molecules. Okay, and different types of electron displacement happening in different molecules. Hope you understand this, and we continue in the next class. One more point, since this is the ortho and para positions in nitrobenzene are positively charged, nitrobenzene is a deactivating group. It is a deactivating group because it will not allow the electrophile to attack ortho and para position. Therefore, it is a deactivating group. The rest are activating group. Okay. Phenol or methyl benzene or chlorobenzene, because in all these cases ortho and para positions are negatively charged. Okay, thank you. We continue in the next class.